Hi, in this video, we will use the area assumptions that we discussed and logic to compute the area of a rectangle whose side lengths are the unit fractions 1/4 and 1/3 units. So, let's proceed as follows. I would like to first sketch a rectangle whose side lengths are 1/4 and 1/3, and it's very convenient to do it in this manner. We look at the horizontal number line and the one marked off on it. We look at a vertical number line and the same length one marked off on it. And now if you take this unit segment and you partition it into 4 equal parts by length, then the length of this part is 1/4. We do the same to this unit segment on the vertical number line. We partition it into 3 equal parts by length. In that case, the length of this part is 1/3. So here's my red rectangle whose side lengths are 1/4 and 1/3. And I would like to assign a number to this red rectangle and call it the area of that rectangle. When I do so, I must follow the rules or the assumptions of the area. So here's how I proceed. I realize that this rectangle really is part of a unit square, and I complete this picture of a unit square. Pull a vertical line, a horizontal line, and I complete that. And furthermore, I draw these vertical lines and horizontal lines. Now we can see how this particular rectangle is part of this unit square. This unit square, you can see, is now partitioned into 4 times 3 rectangles. Why is it 4 times 3? Because we had partitioned this unit segment into 4 equal parts, and we use those parts to create those lines. That's how we get 4 of these strips. Similarly, we get 3 of these strips, and that's how we get our 4 times 3 or 12 rectangles. Notice another thing about those rectangles. Each of these rectangles has a side length of 1/4 and 1/3. So each of the rectangle is congruent to the rectangle. You can visualize picking up each of these rectangles, sliding it, and laying it exactly on top of the red rectangle. So, by assumption number 3, the area of each of these rectangles is in fact exactly equal to the area of a red rectangle. So we have 12 copies of the areas of the rectangles. Together, the 12 copies of that area make up the area of the unit square, which by assumption number 2 is 1. So from there, we can conclude the area of this rectangle must be 1/12, because 12 copies of 1/12 is equal to 1. We can also visualize this argument using the number line. Look at the unit segment on the number line. The 1 could be the area of a unit square. So the 1 on this number line now represents the area of a unit square. The word area is important. We don't want to say 1 is the unit square, because unit square, as we discussed, is a region in the plane. It's a collection of points. It's a physical piece. It's not a number. But the area of a unit square is a number, and it's 1. So here we represent that. So partitioning this unit square into 12 rectangles in the manner I described can be mimicked here, like partitioning this unit segment into 12 equal pieces. The area of each rectangle here is exactly the same. That corresponds to the length of each of these tiny segments being exactly the same. And we can see here, because we partition this unit segment into 12 equal pieces, the length of each tiny piece is in fact 1/12 units. So we go back here. What is the area of each of this rectangles, or in particular this red rectangle? And that corresponds to the length of this tiny segment, which is 1/12. So we can see the connection between the two. 12 copies of 1/12 is 1. Here too we see the same thing. 12 copies of this number 1/12, which is the area of this rectangle, gives us the area of the unit square. So even though here I've discussed a very special case where the side lengths are 1/4 and 1/3, if you go through this argument, you can see that even if I change these numbers 1/4 and 1/3 to other unit fraction, you can carry out the same discussion. That leads us to this theorem. Suppose m and n are non-zero whole numbers, then the area of a rectangle whose side lengths are 1/m and 1/n by this argument is in fact 1/m times n square units. So keep that in mind about this theorem. In the next video, we will look at rectangles whose side lengths are any fractions. They need not be unit fractions with 1 in the numerator. We'll explore that in the next video. Thank you.